Welcome to my mathematical analysis presentation. My name is Alethea Lim, and I'll be presenting the proofs to the Darboux sum comparison lemma and the Darboux sum convergence theorem. We will begin by proving the Darboux sum comparison lemma. We will then use this lemma to prove the Darboux sum convergence theorem. The Darboux sum comparison lemma is as follows. Suppose that the function f on a closed interval ab to the set of real numbers r is bounded. That means that fx is between some negative capital M and a capital M in this closed interval AB. So let P be a partition of closed interval AB that has k partition points. Let P star be any other partition in this closed interval AB. We now define E, the error, to be 4k capital M times gap P star. We want to prove that the Darboux lower sum of Fp star is greater than or equal to the Darboux lower sum of Fp minus E. And the Darboux upper sum of Fp star is less than equal to the Darboux upper sum of Fp plus E. Here's a visualization of the Darboux lower sums. We first have a partition P with k partition points. We then take the Darboux lower sums and it looks like this. We now have a partition P star with more than k partition points. And a Darboux lower sum is this. Putting the graphs side by side, we note that the Darboux lower sum when the partition is P is less than the Darboux lower sum when the partition is P star. Well, this is so because taking the lower sum means we're taking the infimum in each set in the partition intervals in a closed interval AB. In P star, we have more partition points. Hence, we can fill up more of the white spaces under the graph fx. For partition P of x0, x1, x2, all the way to xn, of the closed interval AB, we define the gap of P, otherwise denoted gap P, to be the maximum of the interval between any two consecutive points, where I is between 1 and n, and we look at the distance from xi to xi minus 1. We now begin with the proof. Let xi minus 1 and xi be two consecutive partition points of P star. We have two cases. In the first case, there is no P points in this closed interval xi minus 1 xi. P points are the partition points in the partition P. On this closed interval xi minus 1 xi, the Darboux lower sum of Fp star is greater than or equal to the Darboux lower sum of Fp. We have seen this in the visualization. Here, we use the fact that the infimum of a smaller set is greater than or equal to the infimum of a larger set. There are more partition points in P star, hence, the infimum in these partition intervals can never be smaller than the infimum in the partition intervals of P. In case 2, there are some P points in closed interval xi minus 1 and xi. So in this interval, the absolute value of the Darboux lower sum of Fp star minus the Darboux lower sum of Fp is less than equal to 2 times capital M times the interval xi minus 1. Rearranging, we get that Darboux lower sum of Fp star is greater than or equal to the Darboux lower sum of Fp minus 2 capital M times xi minus 1. Here we use the worst case, which is when the function takes the upper and lower bounds m and minus m. Note that if P contains k points, then the number of intervals in case 2 must be 2k minus 2, because the first and last intervals must be a partition point in both P and P star, and is hence in case 2. Taking the sum over all intervals in P star, we get that the Darboux lower sum of Fp star is greater than or equal to the Darboux lower sum of Fp minus 2 capital M times 2k minus 2, which is the number of intervals, and times xi minus 1. We then know that gap P star is the maximum length of the intervals. So we have that the Darboux lower sum of Fp star is greater than or equal to the Darboux lower sum of Fp minus 2m 2k minus 2 gap P star. And the third line gives us that the Darboux lower sum of Fp star is greater than or equal to the Darboux lower sum of Fp minus 4mk gap P star. When we take E, the error, to be 4mk gap P star, we get the desired result which is that the Darboux lower sum of Fp star is greater than or equal to the Darboux lower sum of Fp minus E. We now look at the Darboux upper sum visualization. So for Darboux upper sum, we still have partition P of k points and Darboux upper sum, and the partition P star with more than k points and a Darboux upper sum. Putting the graphs side by side, we can see that the Darboux upper sum when the partition is P is greater than the Darboux upper sum when the partition is P star. Similarly to before, we let xi minus 1 and xi be two consecutive partition points of P star. In case 1, there are no P points in this closed interval. Hence, we get that the Darboux upper sum of Fp star is less than or equal to the Darboux upper sum of Fp. We use the reasoning that the upper sum considers the supremum, and the supremum of a smaller set, which are some of the partition intervals in P star, is never greater than the supremum of a larger set, which applies to some of the partition intervals in P. Now moving to case 2, there are some P points in this closed interval. So when we take the absolute value of the upper sum of Fp star minus the upper sum of Fp, we see that it is greater than or equal to 2m xi minus xi minus 1. Here we consider the worst case, where the function takes the lower bound and upper bound. We see that taking the summation over all intervals in P star, we get that the Darboux upper sum of Fp star is less than or equal to the Darboux upper sum of Fp minus 2m times 2k minus 2, which is the number of intervals, times xi minus xi minus 1. Since we know that the maximum length of the intervals is gap P star, we can plug this in accordingly. After some rearrangement, we get the third line, which is that the Darboux upper sum of Fp star is less than or equal to Darboux upper sum of Fp plus a 4mk gap P star. We make our E equal to this 4mk gap P star. Then we get the desired result. We now proceed to prove the Darboux sum convergence theorem. Suppose that the function f from closed interval ab to r is bounded. Then the following two assertions are equivalent. A. The function f on closed interval ab to r is integrable. B. For any sequence p sub n of partitions of closed interval ab such that the limit of n to infinity of gap pn is equal to 0, we have that the limit of n to infinity of bracket ufpn minus lfpn is equal to 0. And therefore, the limit of n to infinity of lfpn is equal to the integral from a to b of f, which is also equal to the limit as n goes to infinity of ufpn. Part B suggests that any sequence p sub n with limit to infinity gap pn equal to 0 is an Archimedean sequence of partitions. We will now need to use the Archimedes-Riemann theorem, which says that let f from closed interval ab to r be a bounded function. Then f is integrable on closed interval ab if and only if there is a sequence p sub n of partitions of the interval ab such that limit of n to infinity of ufpn minus lfpn is equal to 0. Moreover, for any such sequence of partitions, we get the limit as n goes to infinity of lfpn is equal to the integral from a to b of f, and the limit of n to infinity of ufpn is equal to the integral from a to b of f as well. Now this coincides with part B of our previous theorem, and hence we get the result of A just by applying Archimedes-Riemann theorem. In the other direction, from A to B, we first use the fact that since f is integrable, we apply the lemma. Suppose that the function f from closed interval a to b to r is integrable. Then for each positive number epsilon, there's a partition P of the interval AB such that UFP minus LFP is less than epsilon. Now this is a consequence of the Archimedes-Riemann theorem. So there exists a partition P such that UFP minus LFP is less than epsilon. Assume that this partition contains k points. Let P sub n be a sequence of partitions with limit as n goes to infinity of gap Pn equals to 0. Next, we define m so that the absolute value of fx is less than equal to m for all x. We now use the lemma that we've just proven. Darboux lower sum of fpn is greater than or equal to the Darboux lower sum of fp minus 4km gap pn. And the Darboux upper sum of fpn is less than or equal to the Darboux upper sum of fp plus 4km gap pn. So subtracting the Darboux lower sum from the Darboux upper sum, we get after some simplification, that U of Pn minus L of Pn is less than or equal to U of P minus L of P plus 8 km gap Pn. By the lemma on the previous slide, we know that since f is an integrable function, U of P minus L of P is less than epsilon for a chosen epsilon. So taking limit as n goes to infinity, we know that limit as n goes to infinity of U of Pn minus L of Pn is between 0 and epsilon plus limit as n goes to infinity of 8 km gap Pn. But limit as n goes to infinity of gap Pn means that the partition points increases to infinity, and hence the intervals goes to 0. So now we have that limit as n goes to infinity of U of Pn minus L of Pn is between 0 and epsilon. Since epsilon is any positive number, we can take it to be as close to 0 as we want. So limit as n goes to infinity of U of Pn minus L of Pn is equal to 0. This completes the proof. That is all for my presentation. Thank you.